Images, visuals, diagrams. These are how the human brain grasps concepts, by seeing relationships rather than just hearing about them. In this final lesson on set theory, we will explore how to visualize abstract ideas through one of the most elegant visual tools in mathematics, the Venn diagram. Hello and welcome to the fifth and final lesson on set theory in our high school algebra series. My name is Joydeep Ghosh and I am a theoretical physicist. The story of Venn diagram begins with John Venn, an English logician and philosopher. In his 1880 paper titled On the Diagrammatic and Mechanical Representation of Propositions and Reasonings, he introduced some overlapping circles to represent logical relationships between sets. Interestingly, his work went largely unnoticed for decades, until the 20th century, when educators recognized its power for teaching set theory. Today, Venn diagrams are everywhere, used not only in mathematics, but also in logic, statistics, computer science, and even everyday reasoning. Their visual clarity helps us see how sets interact, and this understanding will form the foundation for many algebraic ideas we will explore next in our subsequent lessons. So without further ado, let's dive into the details. Okay, so in our final lesson today, we will discuss how to visualize the different sets and set theoretic operations using a method called Venn diagram. So in order to work with Venn diagram, we will take an example. So let's say our universal set U is a set of single digit numbers, so 0, 1 all the way to 9. And let's say A is a subset of the universal set with single digit prime numbers, so 2, 3, 5, 7. B is another subset with single digit perfect squares. So 0 is a perfect square because 0 square is 0, 1 square is 1, 2 square is 4, and 3 square is 9. So 0, 1, 4, 9. And finally, let's say C is another subset with single digit odd numbers, 1, 3, 5, 7, 9. Okay, great. So in Venn diagram, the way the convention works, we represent the universal set using a rectangle like this. And the colors here denote, colors will exactly correspond to the way I use the color convention to define these examples, U, A, B, and C. Okay, so this rectangle corresponds to the universal set, and universal set is always represented usually by a rectangle. Great. Now, the way to think about is the different elements of a set are represented by points. So for example, you can say that there is a point here, and let's say this point corresponds to the number 8. Okay, and I can say that because 8 is an element of U, which in Venn diagram notation means the point corresponding to U must be inside the rectangle that corresponds to the universal set. So don't think of it this way, that each and every point inside the rectangle correspond to an element. So that's not the way of doing it. This is more, there is no geometric meaning. It is more like a visualization technique, which is for our convenience, which essentially says that the elements correspond to some points, and those points have to be inside the diagram. It's not necessarily true that each and every point correspond to some element, right? Because there are infinite number of points, and we're talking about finite sets. Good. So let's, so just another example we can take. Let's say this is another point that corresponds to 6, and that makes sense because 6 is also an element of the universal set. Now, any subset inside universal set is represented using a circle. So let's say this is my A, okay? And let's say this point corresponds to 2, this point corresponds to 3, this point corresponds to 5, and this point corresponds to 7. Great. Now, if I have to draw C, what I'm going to do is I have to draw it in such a way so that it also includes 3, 5, and 7, right? Because we have 3, 5, and 7 here. So let's say I draw it like this. Okay, another circle, that is my C. And I made sure that 3, 5, and 7, not only they are included in the blue, that is the set A, but also they are included in C, the way C is defined. But C also has some additional elements, for example, 1 and 9. So let's say this point is 1 and this point is 9. Great. Now we have to draw B, and in Venn diagram notation, B actually includes 1 and 9. So let's draw it carefully like this. Okay, so definitely 1 and 9 are also included in B, but B has some additional element. For example, this point corresponds to 0 and this point corresponds to 4. Okay, so this is the way how you can visualize. And as I mentioned, it's not true that each and every element has to be, each and every point inside a diagram, circle or rectangle, has to be an element. It's the other way around. um, any element must correspond to a point inside that diagram. Okay, that's the way to think about it. Okay, now let's quickly see how to visualize the union and intersection under the Venn diagram notation. So let's say this is our set A and this is our set B. Now union must correspond this entire region that uh, is included in either A or B, right? So that's the union. So that is union, and the intersection uh, is this overlapping area. The intersection is this overlapping area denoted by this sign, and this makes sense, right? Because that's how the definition of union and intersection goes, but we can visualize it right now using this Venn diagram convention. Good. So having said that, what about A minus B, the difference between A and B that we touched upon, but we never justified or explained the details about it. So A minus B, intuitively speaking, should contain the elements that are in A but not in B, right? As if you are subtracting the elements of B from the elements of A. So in set builder notation, we can write that n such that n belongs to A and n does not belong to B. Okay, both of these conditions should be satisfied, right? That's the intuitive definition, but we also said, and we never justified that is exactly same as A intersection B complement. Okay, now let's see that under Venn diagram notation, if we can see that. So let's say this is our universal set U, and just like the previous description, this is my A and this is my B. Now A minus B, the way I'm representing it in the set builder notation, it should correspond to this segment, this region, right? Because any point in this region actually belongs to A but not in B. So this region must correspond. So this region must correspond A minus B. But now you can see that this is exactly the region that is also A intersection B complement, because this region
is also the overlapping, exists in the overlapping area because it exists in A, but it also exists in B complement because it's not included in B. So this is in the overlapping area of A and B complement, which is the section in the entire universal set outside B. So that actually gives us a visual proof that y A minus B is same as A intersection B complement. Okay, so the final topic of discussion today is to go over a slightly non-trivial exercise, and let's see if we can view that using Venn diagram. So here is our universal set U represented by this rectangle, and this is my set A, and this is my set B. Now let's shade the region which is A union B complement. So A union B complement. Okay. So if I do that, then as you can see that this entire segment that avoids A and B is actually the complement of A union B, right? So this entire segment that I am shading using green. Now let's shade only the A complement part. It will look similar, of course. Everything outside A union B will be shaded, but since it is A complement, I'll actually shade the segment that is inside B as well. So the yellow denotes the segment that is A complement, and similarly let me shade the area that is B complement. So of course everything outside will be part of it, but also the area that is inside A will, but not in B, of course, that is also going to be part of B complement. Now if you do that, then notice that of course the green denotes A union B complement. Blue actually denotes the B complement, and yellow denotes A complement, right? Now notice that A complement intersection B complement. This is the overlapping area between the blue shaded area and the yellow shaded area that coincides with the green shaded area here. Okay, if you can see it, just work out by yourself and you should be able to. But as you can see here, that all the lines that are going through A, they are blue, and all the lines that are going through B, they are yellow. And therefore, the outside A and B, there of course there we have the green lines there, but also the blue and the yellow lines, right? So the intersection, the overlapping area of the blue shaded area and the yellow shaded area exactly coincides with the green shaded area. That means that A complement intersection B complement is exactly same as A union B complement. Similarly, and this is your homework exercise, you can also show that A intersection B complement is A complement union B complement. Now these two are actually a very important result in set theory, often termed as the De Morgan's law. De Morgan's law, and proving them otherwise, like invoking the Zermelo-Fraenkel set theory that is completely outside your scope, is quite a bit of a logical manipulation that we can completely bypass if we just draw their Venn diagram. Okay, so that is actually the power of this visualization approach that is represented by Venn diagrams. Good. So this actually concludes our discussion on set theory. And in the next lesson, we will start talking about functions. Please go over the materials and feel free to join Owlyard platform if you want to do the practice exercise.